it is permissible to install 15 amp outlets on a 20 amp circuit protected by a 20 amp breaker if certain conditions are met. Firstly, the total load in the circuit must not exceed 80% of the circuit's ampacity. This means 20 amps multiplied by 0.80, which equals 16 amps. Secondly, the length of the wire used to connect the outlets to the circuit breaker panel must be appropriate for the amperage and voltage of the circuit. However, it is not permissible to install a 20 amp ground fault circuit interrupter (GFCI) outlet on a 20 amp circuit that is not dedicated and has 15 amp outlets downstream. The GFCI outlet will trip if the total load in the circuit exceeds 20 amps, even if the 15 amp outlets are not being fully utilized. According to the Massachusetts Electrical Code 527 CMR 12.0, specific regulations apply to kitchen and dining room outlets. All receptacles in kitchens must be provided on individual 20 amp circuits. Receptacles in dining rooms that are used for general purposes such as lighting, appliances, and electronics must also be provided on a 20 amp circuit. Therefore, installing 15 amp outlets on 20 amp circuits in kitchens and dining rooms, and avoiding the use of 20 amp GFCI outlets in kitchens with 15 amp outlets downstream would not comply with the Massachusetts Electrical Code. For the safety and proper functioning of electrical circuits, it is recommended to adhere to several best practices. Firstly, use a dedicated 20 amp circuit for all kitchen outlets. Secondly, use a 20 amp GFCI outlet in the kitchen, either on a dedicated circuit or on a circuit with other 20 amp outlets only. Thirdly, avoid mixing 15 amp and 20 amp outlets in the same circuit unless specifically permitted by local codes and regulations. Delving into the specifics of electrical circuits, it's crucial to understand the implications of mixing different amperage ratings in the same circuit. While it might seem convenient to install 15 amp outlets on a 20 amp circuit, this practice can introduce potential hazards and code violations if not executed correctly. The primary concern stems from the fact that a 20 amp circuit breaker is designed to protect the wiring from overcurrent situations up to 20 amps. If you have multiple 15 amp outlets on that circuit, and the combined load exceeds 15 amps but remains below 20 amps, the circuit breaker won't trip, even though one or more of the 15 amp outlets might be overloaded. This overload can lead to overheating of the outlet, potentially causing a fire hazard. The National Electrical Code, NEC, and local codes like the Massachusetts Electrical Code address this issue by setting specific requirements for the types of outlets allowed on circuits of different ampacities. Generally, it's permissible to install outlets with lower amperage ratings on a circuit with a higher amperage rating, provided that the total load in the circuit does not exceed the circuit's ampacity and the outlets are appropriately protected. However, this practice is often discouraged in residential settings, particularly in kitchens and dining rooms, where the potential for higher loads is greater. In kitchens, the use of multiple appliances like refrigerators, microwaves, toasters, and blenders can easily overload a shared 20 amp circuit, even if individual outlets are rated at 15 amps. This is why the Massachusetts Electrical Code mandates dedicated 20 amp circuits for all kitchen receptacles. Dedicated circuits ensure that each outlet or group of outlets has its own circuit breaker, providing better protection against overloads and reducing the risk of nuisance tripping. Ground fault circuit interrupters, GFCIs, play a crucial role in electrical safety, especially in damp or wet locations like kitchens and bathrooms. A GFCI is designed to detect even small imbalances in current flowing through a circuit, which can indicate a ground fault. A ground fault occurs when electricity flows through an unintended path, such as through a person who is touching a live wire. GFCIs trip quickly, interrupting the flow of electricity and preventing serious electrical shock. In kitchens, GFCI protection is required for all receptacles that serve countertop surfaces. This is because countertops are often near sinks and other sources of water, increasing the risk of electrical shock. Installing a 20 amp GFCI outlet on a 20 amp circuit provides the necessary protection against ground faults, but it's essential to ensure that the circuit is properly wired and that the total load on the circuit does not exceed 20 amps. When 15 amp outlets are installed downstream from a 20 amp GFCI outlet, there's a risk that the GFCI will trip prematurely if the combined load on the 15 amp outlets exceeds 20 amps. This can be a nuisance, especially if it happens frequently. Moreover, it can create a false sense of security, leading people to believe that the GFCI is functioning properly when it's simply tripping due to an overload. To avoid these issues, it's generally recommended to use 20 amp GFCI outlets on circuits that serve only 20 amp outlets. This ensures that the GFCI is properly sized for the circuit and that it will trip only in the event of a ground fault or a true overload. When working with electrical circuits, it's always important to consult the National Electrical Code (NEC) and any local codes that may apply. These codes provide detailed requirements for wiring, grounding, overcurrent protection, and other aspects of electrical installations. Failure to comply with these codes can result in serious consequences, including electrical shock, fire, and property damage. In addition to code compliance, it's also essential to follow safe work practices when working with electricity. This includes turning off the power to the circuit before working on it, using insulated tools, and wearing appropriate personal protective equipment (PPE). If you're not comfortable working with electricity, it's best to hire a qualified electrician to do the work for you. A qualified electrician has the knowledge, skills, and experience to perform electrical installations safely and correctly. They can also help you ensure that your electrical system is up to code and that it meets your needs. In summary, while it may be technically permissible to install 15 amp outlets on a 20 amp circuit under certain conditions, it's generally not recommended, especially in kitchens and dining rooms. The Massachusetts Electrical Code mandates dedicated 20 amp circuits for all kitchen receptacles, and it's always best to follow the code to ensure the safety and proper functioning of your electrical system. Use 20 amp GFCI outlets on circuits that serve only 20 amp outlets, and always consult the NEC and local codes before performing any electrical work. Remember, electrical safety is paramount, and it's always better to err on the side of caution. Understanding ampacity is key to ensuring electrical safety. Ampacity refers to the current carrying capacity of a conductor, typically measured in amps. It represents the maximum amount of electrical current that a conductor can safely carry without exceeding its temperature rating. Several factors influence a conductor's ampacity, including its size, material, insulation type, and the ambient temperature. Larger conductors generally have higher ampacities because they offer less resistance to the flow of current. Copper conductors typically have higher ampacities than aluminum conductors of the same size due to copper's lower resistivity. The insulation type affects ampacity because different insulation materials have different temperature ratings. Conductors with higher temperature ratings can carry more current without overheating. Ambient temperature also plays a role, as higher ambient temperatures can reduce a conductor's ampacity. The National Electrical Code (NEC) provides detailed tables and guidelines for determining the ampacity of conductors under various conditions. These tables take into account the factors mentioned above and provide specific ampacity values for different types of conductors. When designing electrical circuits, it's crucial to select conductors with ampacities that are sufficient to carry the expected load. The load refers to the amount of electrical current that the circuit is expected to carry. This can be calculated by adding up the power consumption of all the devices that will be connected to the circuit. The ampacity of the conductor should be at least equal to the load, and it's often recommended to use a conductor with a slightly higher ampacity to provide a safety margin. Overcurrent protection is another critical aspect of electrical safety. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from excessive current flow. These devices trip or blow when the current exceeds a predetermined level, interrupting the flow of electricity and preventing damage to the wiring and equipment. Circuit breakers are resettable devices that can be tripped manually or automatically in response to an overcurrent. Fuses are one-time devices that must be replaced after they blow. The size of the overcurrent protection device should be matched to the ampacity of the conductor it is protecting. The NEC provides specific guidelines for selecting the appropriate size of overcurrent protection devices. It's important to note that overcurrent protection devices are not designed to protect people from electrical shock. That's the role of ground fault circuit interrupters, GFCIs. GFCIs detect even small imbalances in current flow, which can indicate a ground fault. They trip quickly, interrupting the flow of electricity and preventing serious electrical shock. GFCIs are required in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. In addition to ampacity and overcurrent protection, grounding is another essential aspect of electrical safety. Grounding provides a low-resistance path for fault current to flow back to the source, allowing the overcurrent protection device to trip and de-energize the circuit. Grounding also helps to stabilize the voltage and reduce the risk of electrical noise. Electrical codes require that all electrical equipment and wiring systems be properly grounded. This includes grounding the metal enclosures of electrical equipment, as well as grounding the neutral conductor of the electrical system. Grounding electrodes, such as ground rods or metal water pipes, are used to connect the electrical system to the earth. In summary, ampacity, overcurrent protection, and grounding are all essential aspects of electrical safety. Understanding these concepts and following electrical codes can help to prevent electrical shock, fire, and property damage. When working with electricity, it's always best to consult a qualified electrician if you have any questions or concerns. Their expertise can ensure that your electrical system is safe and reliable. Considering the practical application of these concepts, let's examine some real-world scenarios. Imagine a homeowner wants to install a new 20-amp circuit in their kitchen to power a microwave and a toaster oven. They need to select the appropriate size of wire for the circuit. According to the NEC, a 20-amp circuit typically requires 12 American wire gauge AUG copper wire. This size of wire has an ampacity of 20 amps, which is sufficient to carry the load. The homeowner also needs to install a 20-amp circuit breaker to protect the circuit from overcurrent. The circuit breaker should be installed in the electrical panel and connected to the 12 AWG wire. Before working on the electrical panel, the homeowner must turn off the main power to the house to avoid electrical shock. Once the circuit is installed, the homeowner can plug in the microwave and toaster oven. The total power consumption of these appliances should not exceed 20 amps. If it does, the circuit breaker will trip, indicating an overload. In another scenario, a business owner wants to install a new lighting system in their office. They need to determine the total load of the lighting system to select the appropriate size of wire and overcurrent protection. The business owner calculates that the lighting system will draw 15 amps. They decide to use 14 AWG copper wire, which has an ampacity of 15 amps. They also install a 15-amp circuit breaker to protect the circuit from overcurrent. The business owner ensures that all the metal enclosures of the lighting fixtures are properly grounded. This helps to prevent electrical shock and reduce the risk of electrical noise. These examples illustrate the importance of understanding ampacity, overcurrent protection, and grounding. By following electrical codes and using safe work practices, homeowners and business owners can ensure the safety and reliability of their electrical systems. Now let's explore some common misconceptions about electrical safety. One common misconception is that it's okay to use extension cords as a permanent wiring solution. Extension cords are designed for temporary use only. They are not rated for continuous use and can overheat if overloaded. Over time, the insulation on extension cords can deteriorate, increasing the risk of electrical shock and fire. Another common misconception is that it's safe to work on electrical equipment while it's still energized. Working on energized electrical equipment is extremely dangerous and can result in serious electrical shock or death. Always turn off the power to the circuit before working on any electrical equipment. Another misconception is that ground fault circuit interrupters, GFCIs, are only needed in bathrooms and kitchens. While GFCIs are required in these locations, they are also recommended in other areas where there is a high risk of electrical shock, such as outdoor locations and unfinished basements. GFCIs can save lives by preventing electrical shock. It's important to test GFCIs regularly to ensure that they are functioning properly. A final misconception is that it's okay to ignore electrical codes. Electrical codes are designed to protect people and property from electrical hazards. Ignoring these codes can result in serious consequences, including electrical shock, fire, and property damage. Always follow electrical codes and use safe work practices when working with electricity. In conclusion, electrical safety is a critical issue that should be taken seriously. Understanding ampacity, overcurrent protection, grounding, and electrical codes can help to prevent electrical shock, fire, and property damage. Always use safe work practices when working with electricity and consult a qualified electrician if you have any questions or concerns. Their expertise can ensure that your electrical system is safe and reliable.